Hey, what is up, Honors Chem students? Today we cover 10B, the gas laws. Last time, 10A, we talked about what pressure is, force over an area, and we finished 10A with Dalton's law of partial pressures, PT, total pressure equals the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3, and so on and so forth. Today, 10B, we talk about the major gas laws of Earth. We'll talk about the scientists that discovered them because those gas laws are named for those scientists, and then we'll look at the algebra behind them. And simply said, if you can do KU charts, known unknown charts, and you can do algebra, you will be very successful with the gas laws. So here we go. Boyle's law, first law. We'll do four laws today. Boyle's law involves P and V, pressure and volume, a major law of Earth. And there's Boyle. He was an Irishman. His name was Robert Boyle, and he did an experiment involving a J-shaped tube and different pressures with his multi-story home to see the effects of volume. And that's what a J-shaped tube looks like. He used mercury just like Dalton did, or actually Torricelli did with when he discovered pressure. So, what is this Boyle's law? The relationship between pressure and volume on Earth. Remember, pressure is force over an area. Volume is the amount of substance that something can hold. In this case, the amount of particles a container can hold. And here's how it goes. As one of these variables increases, the other decreases. So, if pressure goes up, volume goes down. If pressure goes down, volume goes up. We know mathematically that is an inverse relationship, also known as an indirect relationship. Pressure in these pictures is caused by the gas particles hitting the container walls. And that could go to your house right now. The pressure in your home as you sit and listen to this would be the gas particles in the air in your room hitting everything in the room, hitting the walls, hitting your computer, etc. And we talked about that in 10A. So in the picture, what happens in the picture is we make that container smaller. So we decrease the volume. We have a high volume in the first picture, and we have a lower volume in the second picture. Now, so we definitely know that the volume is less than 1.53 liters. So in this case, if volume is decreased and the number of molecules, particles stays the same, there will be more molecules hitting the walls per unit. So there's a higher pressure in the second container. So if pressure goes up, volume will go down. So this number will be a number less than 1.53 liters. So what's the algebra behind that? What is the equation for Boyle's law? So here's the exact definition. Yeah, we can worry about that, and we can worry about you understanding that, but here it is. Here are the variables. P1 times V1 equals P2 times V2. So what does this mean? P1 V1, that's the initial set of conditions. So that first container in the previous picture, and P2 V2 are the second set of conditions. And we use algebra to solve an equation like this. So I have to give you 3 out of the 4 variables. And you know in algebra, if I give you 3 out of the 4, you can solve for the unknown, the 4th variable. And that's all Boyle's law and all the other gas laws will be like. So this is the exact same problem from the pictures I just showed you 2 slides ago. 1.53 liter sample has a pressure of 5.6 times 10 to the third pascals. If we change the pressure to 1.5 times 10 to the fourth pascals and the temperature stays constant, what is the new volume? So from this, we have some knowns and we have a definite unknown. I'm going to get out of full screen so I can show you the steps on how you should complete a problem like this. You can hear some geese in the background maybe. My door's open. It's a beautiful day today. But here we go. KU chart. Known, unknown chart. So from that wording, we can say that P1 is 5.6 times 10 to the third pascals. We can say that V1 is 1.53 liters. Reading through the sentence more, we can say that pressure number 2 is 1.5 times 10 to the fourth pascals. And the last question, what is the new volume? We need to solve for V2. I am a big fan of doing the algebra ahead of time before I plug the numbers in. And I don't really care how you do it. I found that doing the algebra first and then plugging the numbers in works better for me. If you feel like you need to just plug the numbers in right now and solve for the unknown, you go ahead and do it. It's up to you. But here is the algebra just before we plug the numbers in. So step 1, I'm going to write Boyle's law down. So there it is, Boyle's law. Step 2, I need to get V2 by itself, and algebraically that means I divide both sides by P2. So there is the algebra. And now I've gotten V2 by itself. I can solve the problem, and that would be step 3. Algebraically plug and chug the numbers. So plugging and chugging those numbers in looks like this. I highly recommend you keep your units there so you know what to label your last problem with, or your answer with. So 5.6 times 10 to the third pascals times 1.53 liters divided by 1.5 times 10 to the fourth pascals. Remember, we said we expected the number to be smaller than the initial volume, 1.53 liters. So we should get an answer. We should know ahead of time we're getting an answer lower than 1.53. Since the pressure went up, the volume had to go down. Sig figs matter, only 2 sig figs. And indeed it did go down. Our final answer is 0.57 liters of sulfur dioxide gas. And that's V2. And it's as simple as that. That's Boyle's law. Let's go to the next law, and let's go full screen again. And that's Charles' law. And Charles' law involves volume and temperature, V and T. This was a French physicist, Jacques Charles, and he discovered this in 1787. And he was also, just an FYI, the first person to fill a balloon with hydrogen and make a solo balloon flight. So kind of the first airman, I guess you could say, using hydrogen gas. So he was big into the gas. Now, Charles' law. Just look at the picture first. Remember, it involves volume and temperature. So I have a specific volume and temperature on the left. If I put a heater underneath this container and heat up the particles, that will cause the particles to move faster, and that will increase the volume. So you can start to see the mathematical relationship is different between volume and temperature compared to Boyle's law. Boyle's law, pressure and volume, was indirect, inverse. Volume and temperature looks like it's going to be direct. And this wording just kind of explains exactly what I talked about already. I increase the temperature, which therefore increases the volume of the container holding the gas. And pressure would be held constant in this case. And the pressure in this picture would be these 2 little weights that sit on top of the container. The big rule with these gas laws is that we must use Kelvin temperature. And you can probably guess why we have to use Kelvin temperature. When we do any of these gas laws, we cannot get negative numbers. If we used Fahrenheit, if we used Celsius, we would get negative numbers. Kelvin scale is the only scale that does not have negative numbers. Remember, to find a Kelvin temp, you add 273 to the Celsius value. So the definition of Charles' law is that, but simply, V1 over T1 equals V2 over T2. So a slightly different look compared to Boyle's law. V1 over T1, that's the initial set of conditions. V2 over T2, that's the second set of conditions. Just like the previous problem, algebraically, I will give you 3 out of the 4 variables, and you will have to solve for the unknown using algebra. So I have a situation. I have a gas at 15 degrees in 1 atmosphere. It has a volume of 2.58 liters. What volume will this gas occupy at 38 degrees and 1 atmosphere? So right now, the first thing you should know, all these numbers, yes, but the pressure stays constant, 1 atmosphere. So I don't have to use pressure anywhere in my equation. It's constant. I take it out. I don't worry about it. Let me go split screen now so you can see the algebra behind this problem. So KU chart is very important. You need to stay organized. So from this problem, the first volume was 2.58 liters. The first temperature was 15 degrees, but we can't use 15. We've got to add 273 to that. And I went ahead and did that, and that's 288 Kelvin. What volume? So there's the unknown. V2 is our unknown. Will this gas occupy at 38? I can't use 38. I've got to convert that to Kelvin. So 38 plus 273 is 311. So there's my KU chart. I have 3 out of the 4 variables. I'm solving for the unknown, in this case, V2. Again, I like to do the algebra with the equation first. So the first thing I'm going to do is write down Charles' law, V1 over T1 equals V2 over T2. And then mathematically, how do you get rid of fractions, a proportional fraction? Well, you should know. In algebra, you cross multiply. So cross multiply meaning to get rid of these fractions, V1 times T2 equals V2 times T1. So now I've gotten rid of the fractions. I can get my unknown V2 by itself by dividing both sides by T1. And there we go. V1 over T2, V1 times T2 over T1 equals V2. And now step 4, I plug and chug my numbers. So that's a 2.58 times 311 divided by 288 to get my final answer of 2.79 liters. Does this make sense? You need to ask yourself every time you do a problem like this, is this legit? Charles' law is a direct relationship. If temperature goes up, volume has to go up. So temperature went up, my answer should be a number higher than 2.58 liters, and it is. So my math is good. I've done it well. My final answer makes sense. 2.79 liters is an increase over 2.58 liters. Third law. Is Gay-Lussac's law. So we had Boyle's, we had Charles, now we have Gay-Lussac, 1802. I assume he is from France. And let's look at a picture again. So in this case, we're only involving pressure and temperature with Gay-Lussac's law. And that means the volume stays constant. So in the picture, the volume never changes. So we have no change in volume. The space inside this container is the same in both of these pictures. So if I increase the temperature, check this out, to keep the volume the same, I have to increase the pressure by putting another weight on top of the container, and that would be the pressure side of this. So temperature increases, pressure increases. We have another direct relationship. If pressure went down, if temperature went down, pressure would go down. Remember, pressure is the result of collisions of molecules with the walls of the container. And remember, temperature involves kinetic energy, so the movement of those particles, which we learned about when we talked about the KMT back all the way in first semester. If temperature increases, collisions occur more often because those particles are flying faster with more velocity, and we would have a pressure increase. So, looks very similar to Charles' law. Only difference is instead of instead of volume and temperature, we now have pressure and temperature. P1 over T1 equals P2 over T2. So P1 over T1, the initial set of conditions, P2 over T2, the second set of conditions. So let's look at a problem. I have a gas in a can. It has a pressure of 3 atmospheres. It's at 25 degrees Celsius. I can't use that. I have to change that to Kelvin. Directions on the can warn the user not to keep the can in a place where the temperature exceeds 52 degrees Celsius. what would the gas pressure be in the can at 52 degrees? Hint, use Kelvin, use Kelvin, use Kelvin. So let's get out of this so I can show you step by step. KU chart, KU chart. Use the KU chart so you can stay organized. From the problem, 3 atmospheres. That's P1. From the problem, 25 degrees Celsius. That's T1. Can't use that. 25 plus 273 is 298. Then the question says, what would the gas pressure be? So there is my unknown, P2. If the can's at 52, so 52 plus 273 is 325. Very similar to the last example problem. Step 1, I am going to write down Gay-Lussac's law. Step 2, I'm going to cross multiply to get rid of the fractions, the proportional fractions. So P1 times T2, cross multiply, equals P2 times T1, cross multiply. Step 3, get my unknown by itself by dividing by T1. So there we go. P1 times T2 over T1 equals P2. And then step 4, plug and chug my numbers from my KU chart. So that's 3 atmospheres times 325 divided by 298. And that will give me a final answer of 3.27 atmospheres. Does that make sense? Let's see. If temperature goes up, what should happen to pressure? It's a direct relationship. Pressure should go up also. If temperature increased, the pressure should increase. We started with 3 atmospheres. Temperature went up about 27 Kelvin. That means that in this case, the pressure went up 0.27 atmospheres. Our answer makes sense. Let's get back to the full slideshow. And that leads to our final law of the day, the final gas law, and that's combined gas law. If you really paid attention to all of these 3 previous gas laws, in the end, they are all related to one another, and we can combine them all together, which makes us have 6 variables in one algebraic problem. So temperature, volume, and pressure all can impact a gas at once, and we can combine these into the combined gas law. P1 times V1 over T1 equals P2 times V2 over T2. 6 variables, obviously. Again, I have to give you 5 out of the 6 variables in the story problem, and through algebra, you will be able to solve for the unknown 6th variable. So let's do a simple problem on this very last one. Very last slide. Helium-filled balloon has a volume of 50 liters at 25 degrees and 1.08 atmospheres. So I can right now start building my KU chart. And from that, V1 liters, that's volume. So V1 is 50.0 liters. T1, 25 degrees Celsius, can't use that. Have to add 273 to that to get 298. And 1.08 atmospheres. Atmospheres would be P1. And then the second part of the story problem, what volume? So right now, what volume? That means I'm solving for V2. That's the unknown. Will it have at 0.855 atmospheres? So that's P2. And 10 degrees Celsius. 10 degrees Celsius is 10 plus 273 to get 283. All right. Let's use the combined gas law. So the first thing we do is write down the combined gas law. And you can see that. I need to get V2 by itself. And the first way to do that is to get rid of these fractions, this proportions, by cross multiplying, just like we did on earlier problems. So that's what it looks like algebraically after I cross multiply. P1 V1 T2 equals P2 V2 T1. I need to get V2 by itself. So I divide both sides by P2 T1. And there we go. Now V2 is by itself. I have 5 variables on the left side. I have my unknown on the right. And that now allows me to plug and chug the numbers from my KU chart. So you need to be really tedious when you do this with your calculator. 1.08 times 50 times 283 divided by 0.855 divided by 298 equals V2. And when I do that, I get a final answer of 60.0 liters of helium. And can I check myself, hypothesize? It's a little more difficult to plan ahead or to hypothesize what your final answer will be when you do the combined gas law, because we have inverse relationships and direct relationships happening at the same time. But overall, my answer does make sense, where my volume increased by 10 liters, even though the temperature went down. The pressure went down enough that the volume went up, according to that. And that finishes off today's 4 laws. If you need to make notes, if you need to make a chart of these 4 laws, write it down on paper, I would do that. I believe it is on your reference sheet also. So obviously your homework today will be to do problems involving these 4 gas laws. Have a good day, and I will talk to you all later.